All right, so is the screen visible for everyone?
Sir, can you repeat a vector? Shortly repeat vectors.
All right, of course, I'll do it quickly. So if we go back here, here is where we were discussing vectors using the idea of displacement, right? So let's quickly revise it here. Revise vectors. Okay, so vectors are simply anything that are dependent on a number and a direction as well. Now, for example, suppose that I have a path that is starting from a point, right? And it's ending at the same point. So I can have this circle, and here this is point A is this start and end point. Suppose this particle travels along this circle, circumference of the circle. So if I'm talking about displacement, then displacement I can draw a displacement vector at every point on this circumference. So for example, if I draw a displacement vector for this point, then it would I think I'll use different colors. Let me use this green color. So displacement vector at this point is this thing. Displacement vector, because you can see that the path is along this direction, so the displacement vector at this point is a tangent, which is like this. At this point, the displacement vector is, because it's going like this, right, it's going in this direction. So the displacement vector is a tangent to this point, which will be in this direction, and similarly over here it's in this direction for the same reasons. Now these are vectors. Now, if we say we start our journey at point A and end at point A as well, so start and end points are A, right? In that particular case, you can see if I take these vectors, this one and this one, and if I add these two vectors together, I'll get 0, right? Because this is pointing in this direction and this is pointing in the opposite direction. So their sum would be equal to 0. Similarly, if I look at this vector and if I look at this vector, then their sum would also be 0 because they're pointing in the opposite directions. So that's why we say that and this will always be the case whenever you start your journey and end it at the same point. Your vectors will always be pointing in the opposite directions. You will always have one vector for which there will be another vector which points in the opposite direction of that vector. So that's more or less vectors, right? And we use the idea of displacement to talk about vectors. So this is really, at this point, this is a displacement vector. But this rule is followed every time. So it doesn't matter what vector you're talking about. You can have any vector, any type of a vector. And this thing is still valid. You can have force vectors, you can have velocity vectors, it doesn't matter, right? So any vector will follow this principle. Okay, so is that clear, Taha?
Yes, clear.
All right. So before we ended last class, we were talking about this thing. We were doing a problem, really, and I'm sure we finished this problem, right? Do you have any question? Any student has any question from anything that we did in the last class?
No questions.
All right. Okay. So no one has any question?
Can you explain velocity a little? I'm still confused about that.
Velocity, right? So this is where we were doing that. All right. So do you understand the concept of speed?
Yes.
Okay. And how about a displacement?
Maybe a little bit. Yes.
Okay, and how about distance? Distance is understood, right? It's just
Yeah.
okay, great. So if I include directions in distances, as you can see over here, if I say that I care about a direction, I want to know in what direction am I moving? Am I moving here or am I moving over here? In that case, you'll still, for example, if you move in this direction, you're still covering some distance, right? So let's say this is some distance. For example, let's say this is 1 meters. But at this point, you're also saying that I'm moving 1 meters to the right. So, and then we can define signatures in our mathematical expressions to define what is right and what is left, because the mathematics does not know at this point what is your right and what is your left. To differentiate between the two, you need to give it a signature, and that's how the mathematics knows what you're defining as right and what you're defining as left. Now, two signatures, so a signature can be either positive or it's negative, and this is good enough for our case because there are only two possibilities, right or left in the horizontal direction, and again there are only two possibilities, up or down in the vertical direction. So something that can be of two types, that is this signature, which can be either positive or negative. So these signatures will work for our case. Now, we are saying that positive is to the right and negative is to the left. This means that if I'm moving to the right, I'll say I'm moving plus 1 meters to the right. And if I say I'm moving minus 1 meters, that is immediately this negative sign is telling you that this 1 meters is to the left. So it's just negative sign is just a way of speaking that I'm talking about the left direction. So when I read this number, mathematically, you will just say it's minus 1 meters. But as a physics student, you would be saying that this is 1 meters to the left. That's what the minus sign is telling you. So that's really displacement. Now we can apply this idea to the speed or to velocity. But really, we are applying this idea to speed, which is becoming displacement. Which is becoming velocity. So when you say, if you understand speed is just how distance changes with time. So that means how fast can I change a distance as the time passes on, right? As a velocity is concerned with the displacement. How fast can I change the displacement, meaning how fast is my distance with direction is changing. So that means you could be either moving to the right or to the left. So again, plus signature would be telling you that you're moving to the right with a particular value of speed, and minus signature would be saying you're moving to the left with a particular value of speed. So it could be written as, for example, you're moving with uh, let's just say you're moving at 1 meters per second for simplicity. Now, if I put a negative sign, this is now velocity. In speed, there is no negative or positive. In velocity, there is negative, and this negative sign is telling you really that you're moving to the left.
So is
So again,
velocity always measured in a straight line?
no. Now, so of course, these directions, we're talking in general at this point that we're talking about a straight line, but you can associate this with any direction. For example, let me give you an example. Suppose that I'm moving like this. But even for this line, you can see exactly at 180 degrees, there is an opposite to this thing as well. So you'll define a coordinate system on the side of the paper. You'll say that this way is positive, and then you can say this way is negative. And again, the rest is simple because you'll just use positive sign if something is moving. For example, it's like a hill, a slope, and there is a car which is moving on the slope. You'd be saying that if it's moving in this way, it's moving plus for example, let's say 2 meters per second. And if it's moving this way, then it's moving minus whatever the velocity is. Suppose it's 2 meters per second. So you always, there are two directions, right? For whatever line that we draw, there can be two directions on that line. One in going in the one direction, and the other one is exactly 180 degrees to that direction. So there are always two options, and that's why this idea of signatures work, because we have two signatures and there are two directions, so we can just associate one signature with each direction. So is that clear?
This also works with circles, right? Because you can go clockwise or anti-clockwise.
Exactly,
Going clockwise will
very
be
good point.
positive, and going and
Yeah, very good point. Very good point. So you can choose a particular direction for that as well. You can say that if I'm going clockwise, clockwise really means, so for example, let's go back to this example that we were doing. So this is a circle, right? I'll just draw it again over here. So if I'm going on this circle, if I start my journey from this point and I go in this direction. Now, what is that direction? That direction is, we say that it's anti-clockwise, or let's first discuss clockwise. So discussing anti-clockwise would be more simple. If I'm moving in this direction, so I start from A, I move like this, and then I come back to point A. Now, this is how the hands on the clock move, right? They move in this direction, as we all know, right? So here we have 12, then at some time we have 1 o'clock, then 2 o'clock, then the timing of your class, 3 o'clock, which people should know by now so that they can be on time. And then we have 4 o'clock, 5 o'clock, 6 o'clock, and you get the point, right? So that's why if you're moving in this direction, then it's called clockwise direction. If you're moving opposite to this, which would be in this direction, so it would be something like this. So that's called anti-clockwise. Now you can just assign a signature to both. Maybe you can say that, perhaps you might say that clockwise is positive. Then the only other option is anti-clockwise, and that's why a positive and negative signatures work in this case as well. So these things this will always work, because there are only two possible states: up or down, left or right, clockwise, anti-clockwise. So there are always two possible states, right? And so the idea of signature works for that reason. So is that clear? Urva, is that does this make sense now?
Yeah.
Okay. Okay, perfect. Good job. All right. So okay, so any other question? Okay, I'll assume then there is no questions. So we'll do another, I think we should do another example. And after that, we'll start the topic of graphs. So let's quickly do an example that will revise some of the things from the previous class as well. Suppose that I have a car, and this car is going to travel along this straight line. And suppose the distance, the car is going to start its journey from this point, right? And is going to move like this. Suppose this much distance from the starting point to this point, the distance is, let's say, 840 meters, for example. Now we say that the car is moving at a constant speed, which means every point that it will be moving on this line, the speed will be same at every point on this line. Now we are saying that it is, velocity is 35 meters per second. This is the constant speed with which the car is moving to the right direction. Then we say at this point, when it reaches this point, right? I think I'll use another color. So when it reaches this point, this green line, the driver applies brakes. At this point, the driver is going to apply brake. what happens when a driver applies brakes in the car? The car slows down, right? So the car will start slowing down, which means that the velocity at this green line, it would start decreasing. The velocity would start decreasing. What that means is there is some negative acceleration, which means that there is sometimes it's also called deceleration. So which means that the speed, instead of increasing the speed, you are really decreasing the speed. So that's the opposite of an acceleration, which means it's just a negative acceleration working to decrease the speed. So, and then at some point, at some distance, the car comes over here at some point and it stops. It comes to a rest. There is a statement used always, rest. This means that the car stops, which would mean that the velocity becomes 0. Right? So it's stopped, distance is not changing at all. So distance changed would be, or displacement would changed would be 0. And that's why velocity would be 0, because velocity is displacement divided by time. All right. Now, from this point, when it starts to decelerate, it takes from this point to this point, when it comes to rest, it takes 7 seconds. So are you understanding the question? The car started its journey from a point and it covered a distance of 840 meters, moving at a particular speed of 35 meters per second. Now it was moving at this speed, and then when it covered this distance, 840 meters, suddenly the driver applies brakes and the car slows down, keeps slowing down, and then eventually stops. Now, the time that it takes when the driver applied brakes to when the car stopped is 7 seconds. So it took 7 seconds for the brakes to completely stop the car. So when the car is stopped, the velocity is 0 meters per second. So is the stage that I set for the problem, is that clear?
Yes.
Okay, great. So the first thing, let's try to figure out the first thing, the time for which the car was moving at this constant speed, right? So time for which car is moving with constant speed. So what do you think? How should we go about this? We know that the car is going to be moving for a constant speed until the driver applies brakes, because as soon as the brakes are applied, the velocity starts falling, decreasing. Sorry, are you saying something?
To answer this question, you divide the velocity by the distance?
All right, so yes, we'll have to find the time taken, right? So we know that the velocity is given as, all right, so first let's see what are we given. We're given, of course, Taha, you're right, but let's try to understand why will we do that, right? So the car is moving for a constant speed up until 840 meters, and then he applies the brakes. So velocity starts changing. So velocity is not constant anymore when the brakes were applied. So you have this velocity, which is constant. So let's write that down. We have 35 meters per second. And this constant velocity is only going to be there for 840 meters, because after that the brakes are applied. So displacement is 840 meters.
Velocity
right?
is moving in one direction, right?
Yeah, it's moving to the right. Yeah,
Mhm.
it's just the car is just moving to the right. So, right. All right. So, and we are now required to compute the time taken. And as Taha said, it would be done by using this equation. We don't know the time, right? So we'll just write it like this. Now we'll see what relates these quantities. So we know that's the equation V equals S by T. We discussed this equation last time as well. So that's simply 840 meters divided by time, which is equal to velocity, that is 35 meters per second. Now let's just solve this for t. So we'll rearrange the equation. T will go there, 35 will come here, and it will be divided. So it will be 840 meters divided by 35 meters per second. Meters cancel out, seconds will come upstairs, and this will become 840 divided by 35.
It's
That's
24.
24. Right, amazing, thank you. That's 24 seconds. So it would take what, let's see, what does this mean? This means that the car is going to be moving 35 meters per second. And since the driver started its journey, up until the time he applied brakes, he was traveling for 24 seconds. And as soon as 24 seconds passed, the driver pressed on the brakes and started to decrease his velocity or speed.
Yes.
All right. So is that clear for everyone?
Clear.
Yes.
Okay, wonderful. So moving on to part two, let's say, let's try to find, so one of the things that we found is the time taken. Now, what the other thing that we could find is the value of this negative acceleration. When the brakes were applied, how fast did the speed start decreasing? That's negative acceleration or deceleration. How fast did the speed start decreasing? So if you think on these words in English, you can just figure out the formula for this as well. So it's just a matter of converting English into mathematics. So we want to compute the acceleration, right? So the acceleration when brakes were applied. So I'm just calling it acceleration in general. It could be negative acceleration or it could be positive acceleration, but we'll see that it's negative indeed, right? Let's see how. When brakes are applied. So we know that I'm trying to have this figure here, so I'll not go down. So we know that acceleration would be the change in velocity divided by time, because it means how fast is the velocity changing as time progresses. So that is, acceleration is change in velocity divided by the time it takes to change that velocity. All right, so we know finally what happens, the car comes to a stop. So at that point, the final velocity is 0, right? So we can say that V2 is 0. What is V1? V1 is the velocity which was right there just before the brakes were applied. And that velocity was this constant velocity of 35 meters per second. So that's the two velocities. And in the question we have that when the brakes were applied, it takes 7 seconds for the car to stop or to come to a rest, which means that the time it takes to change this velocity from 35 to 0, meaning time taken for the vehicle to come to rest, is 7 seconds. So it's just a matter of putting these values now. Change in velocity is the final velocity, which is 0, minus the first initial velocity, which is 35 meters per second, divided by the time that it takes to cause this change is 7 seconds. So we see that this just becomes minus 35 by 7 meters per second divided by second, which is just minus 5 meters per second squared. Now, this
Yes.
is the acceleration. And the negative sign in this expression is telling you that the velocity is decreasing. So the acceleration is negative. So acceleration is working to decrease the velocity of the car. So is that clear for everyone?
Clear.
Is it negative
Okay,
because there's
good.
a negative sign before 35? Next to 35.
Yeah,
No.
that appeared mathematically, that appeared. So but physically the reason for this negative sign appearing is that the velocity is decreasing, right? Because you can see that the final velocity is 0, and initial velocity is 35. So that's why we got a 0 minus 35. How can the final velocity be 0 if initial is 35? Only in this way, if the velocity was decreasing, right? And it is decreasing with 5 meters per second every second. This result, physically, if you think about it, it is telling you that the velocity of the car decreases by 5 meters per second in every second. So I'll just write it down over here. Velocity decreases by 5 meters per second every second. So every second that passed when he applied the brake, the velocity dropped by 5. Then again, after another second, it dropped by 5 again. Another second passed, it dropped by 5. So it took 7 of these seconds to completely drop the velocity to 0 meters per second. So is that clear?
Yes.
All right. So does that make sense to everyone in the class? All right. So I'll assume that this is clear for everyone. So we can move on to the next topic in kinematics, which is of graphs. Let's spend a little bit of time in understanding what a graph really is. So graphs are there as a tool. It's a mathematical tool that we physicists use to visualize our problems, right? So it helps us in visualizing what is happening, and we'll see how that is, right? And another thing is, how do we visualize these things? We visualize these things by relating two variables. These variables can be anything. Velocity with time, so you can see how velocity changes as time passes, or displacement with time as well. How is the displacement changing as the...
Sir,
Yes.
can it be acceleration by time, like
Exactly.
35 meters?
Mhm.
35,
Yes.
and when the man steps on his brake, it decreases every negative 7, every 5 meters. But this one, 5
Oh,
meter
you're
per
talking
second
about
square.
this. You're talking about the last problem, right?
Yes, can you make a
This
graph
one.
of this one, for example?
Yes, of course we can make a graph, but we'll do that. Remind me when we are talking about acceleration time graphs, but let's first quickly start from these displacement time and then velocity, and then we'll discuss acceleration time graphs as well, right?
Okay.
So at that time, we'll come back to this example and we'll draw an acceleration time graph for this. But the acceleration time graph for this should be a constant. Just telling you, you can think about it. It will be a constant line,
Yes.
straight
Yes.
constant line, right?
I understand.
Parallel to the x-axis. Okay, perfect. All right. So coming back to this thing, we are talking about graphs, and they're there to help us visualize things in a much better way. So graphs are actually very friendly for us, right? Even though maybe if you don't know about graphs, they might appear as daunting and scary, but they're actually very friendly. So they are friends. Now, they help us visualizing things by relating two variables. We'll see that, for example, if I have displacement, I can see how this displacement changes with time. And so the graphs in general, they could take any shape. By that, what I mean is, for example, mathematically speaking, mathematicians, they don't care about any quantities. They don't care if we're talking about displacement, time, whatever. So they'll just give them any arbitrary names. These two lines, they're called axes. And normally mathematicians, they define the horizontal axis as an x-axis, and the vertical axis is defined as the y-axis. Now, these two alphabets are completely arbitrary, which means they can be anything. It doesn't matter. There's nothing special about this axis that we are calling it x-axis. The names or the letters assigning to them is completely up to your choice, right? I could have called this thing, you could have called this thing capital A and this thing capital B. Doesn't matter as long as you know what these things, what these are, right? So what these are, let's come to that point. What are these axes? The axes should always be perpendicular to each other, any axis that I draw. So the other axis that I can draw, which would be perpendicular to these, could be an axis that is kind of coming out of this page, right? Out of this screen towards you, because that would also be perpendicular to these axes. But let's not get into that at this point. That's the third dimension, and we'll just stick to 2 dimensions. All right. So one thing is that these axes should be always perpendicular to each other. And the reason for that is that there should be no part of x in y. You can see that x is completely independent of y axis. Y is vertical, x is horizontal. All right. So that's how mathematicians define axes. Now for physics, we normally take time on this axis and the quantity that we want to see, how will that change, we take it on y-axis. So how will this q change as time passes? I said it as a q in general for any physical quantity, right? So displacement, velocity, acceleration, force, doesn't matter. All right. So when we're talking about motion, normally on x-axis we take time. All right. So is that clear, by the way, for everyone? Okay, I'll assume that it's clear. Now we can have different shapes of. Yeah, sorry. Okay, so we can have
Sir, my
different
mic.
shapes of graphs, right? So maybe it could be a straight line. It could be any curve. It could be something like this as well. So I'm just drawing random lines on the graph, right? So it could be something like this. It could be like this as well. So all of these lines, they are very random. So I'll just give them different colors quickly. So these are different types of graphs. All right. So the point was here to tell you that the graph can take any particular shape. Let's now move on to the main thing, which is the first type of graphs that we'll see are displacement time graphs. All right. So displacement time graphs, the name really says most of the things. It is a graph between displacement and time. So for example, now, well, not an example, I'll actually tell you, this graph basically gives you a relation. So we talked about a graph should be giving you a relationship between two quantities, right? So the two quantities over here are relation between displacement. I'll just use small s for that, displacement and time, small t for time. So the graph could be, so let's talk about the axes first. So on the horizontal axis, I'll have time, and on the vertical axis, I'll plot displacement. Displacement is measured in meters, so that's what the slash is showing, slash seconds for time, because time is measured in seconds. All right, now the graph can have different types of shapes. Let's come to that point. For example, if I say that the graph has this shape. So from this, what do you see? We see that at every point in time, as time passes, the displacement is increasing. So suppose if this was T1, the value of displacement here would be some S1. Some more time passed, T2, the displacement increased by some value. So it is, maybe it is some S2. And similarly, more time passed, T3, and the displacement increased again to some S3. Now, the ratio of how this displacement is increasing is a fixed value at every point on this line, because this line is a straight line. There are no bends, no curves, nothing of that sort in it. It's just a straight line. It is minding its own business, and hence there are at every point the ratio of how displacement changes with time is a fixed value, and we'll see what do we mean by that. There's something that we can compute for this from this graph, and that is the slope of this graph, mathematically speaking, at this point. So the slope, which is also called the gradient of the graph, is represented mathematically by the values on y-axis. So change in the values on y-axis, which is really the vertical axis, divided by the change in values on the horizontal axis. Now, if we associate this thing to the displacement time graph, then this thing becomes change in displacement divided by change in time, right? Because on okay, so we have less than 1 minute apparently. Is this clear so far?
Yes.
The idea of graphs and displacement time graphs. So I think the class will end now anytime. So let's just wrap everything up quickly. We just in the next time we'll be doing displacement time graphs, and we'll be doing some examples for this velocity time graphs. We'll try to